Welcome everybody, Mr. Allen here. Today we're going to look at investigating reciprocal functions, or specifically how reciprocal functions relate to the original function. The one thing to sort of note here is I don't want you to think of this as a memorization process. When I have this, then I get that in the reciprocal, or if the original looks like such and such, then the reciprocal will be, it's not like that. What we want to understand is what a reciprocal function is. And here we sort of have two as a starting point, just as an example to look at. So basically the reciprocal function is just the original function, 1 divided by the original function. It could also be something where we have a 5 divided by the original function, or any other constant value divided by the original function. That would just mean that the original function maybe had a fraction involved with it. But the big thing is to sort of recognize this is where all of our information is going to come from. And you want to remember that f at x is just y. So we're saying in my original equation here, the way I calculate my y value is by subbing in some x values for here. I calculate the y value, and that will establish what my original graph looks like. Similarly, when we go to the 1 over f at x idea, to the reciprocal, essentially we're just taking the old y values and we're dividing 1 by each of them. And so we're going to get 1 divided by whatever the y value was at a specific x value in my original. And then we'll sort of determine from that how that a new graph will react. So we'll just look at these key points one at a time. Our first key point, pretty obvious one, our x-intercepts. And so once again here, recognize the red graph is my original graph. So I'm kind of focusing on what's happening at these x-intercepts here and here. My original, of course, the y value is 0, f at x is 0. And so the question is, what happens when we have the reciprocal? 1 over 0 essentially is what we're going to end up with. And of course, that's a value that we cannot calculate. And so what we'll end up with is an asymptote in that location. Or in this case, in both of those locations, because we do have two of them. Now again, not a memorized thing, just a think about it thing. I had a 0 for my y value in my original. I'm calculating my reciprocal's value by doing 1 divided by 0. I cannot do that. I end up with an asymptote, a vertical asymptote specifically, basically a location that I cannot access on my graph. I cannot pass through on the graph. So the next thing we're going to look at here is what happens when my graph was positive. F at x is greater than 0. Well, for dividing 1 by a positive value, we of course will end up with a positive value as well. And so in this section where my graph is positive, my original graph is positive, you can see that the new graph is also positive, which hopefully should make sense. 1 divided by a positive number does get me a positive number. I didn't state it, but similarly, the opposite is also true in the negative sections of my graph. Over here and over here, if my original was negative, my reciprocal is also negative. Next thing to look at, what happens as my graph is increasing or decreasing? So if my original graph is increasing, where's that occurring? So that's occurring basically in the first half of the graph. In this section of my graph, my y values continue to go up, to increase, up to about there. So looking at the reciprocal now, from left to right, my graph is hard to tell here, but it is decreasing, and then it decreases much more quickly. The graph happens to jump across the asymptote, but as soon as it does, it starts to decrease again, and again continues to decrease to basically the midpoint of the graph right here. So the original was increasing, the reciprocal is decreasing, and you can see that in the second half of the graph, the opposite is true. My original graph was decreasing, my reciprocal is increasing. Okay, so next thing, we're looking at horizontal asymptotes. Now again, basically horizontal asymptotes for reciprocal functions will always occur at 0. But once again, we'd like to know kind of why and be able to figure that out if by chance we don't remember. And so the key here is to recognize what a horizontal asymptote is. It's not the same as a vertical asymptote. A horizontal asymptote is essentially a value that my graph approaches way out here, way out here. And essentially, if we look at our original equation then, what we're saying is we have 1 divided by, again, whatever the y values are, when x is extremely large. So that means we're going to have extremely big values going into our denominator. Whatever our calculation is, here it is a square. When we put extremely large numbers in there, whether positive or negative, they always become positive and then get multiplied by the -1 out front. And so I'm getting 1 divided by some extremely large values magnitude-wise, whether they're negative or positive. I'm going to get 1 divided by a big number, and so I'm going to end up with a value that is very, very close to 0. And again, that doesn't really matter whether I'm going left or right in this case. My y values are getting to be extremely large, again, magnitude-wise, absolute value-wise, and so 1 divided by any extremely large number will be close to 0. If it happens to be that it's a negative number, then we will know our graph will be approaching from just below. We'll be getting numbers like -0.00000000001. If the value happens to be positive, then we'll end up with values that are slightly above 0. But again, just overall, my horizontal asymptote is a value that I'm approaching when I use extremely large values of x in the negative direction or in the positive direction. And so I can get a pretty good idea that I'll have a very big number. I'm dividing 1 by a very big number. And of course, again, that will be very, very close to 0. And then last key point for this side anyways, sort of what happens where we have local maximums and local minimums. Well, we sort of have a local maximum here on our parabola. And of course, that means that that's the biggest number in this section of the graph. And so when I'm dividing 1 by the biggest number I can, I end up with the smallest number I can. And so where there is a local maximum on my original, there will be a local minimum on my new graph. And once again, the opposite is true as well. If I did have a local minimum here, because it would be the smallest number, 1 divided by the smallest number I have, will get me the biggest number on the second graph. Last key points, and I sort of thought this was the easiest way to just show these. Basically, if you look at the intersection points here for our two graphs, what we'll see is the y values in all cases are either 1 or -1. And then once again, just sort of thinking about it mathematically, if the end result of this is a calculated value of 1 or -1, then the calculated value of this is 1 divided by either the 1 or the -1. We should get the exact same value. So when the y value is 1 or -1, our reciprocal will intersect it, also be at 1 or -1. So now we're going to put it together. We're going to sketch the reciprocal for this original red function f at x. Without seeing the equation, all I can do is kind of go through what I understand about reciprocals. So I left my little hints at the top for myself. My first key value will be where the 0 was on my original, where the zeros were, I suppose, there are two of them. In my original function, I will place my vertical asymptotes. So again, the original value, the original y value was 0. 1 divided by 0 is a calculation I cannot do. That's where my vertical asymptotes occur. There are spots on the graph that I cannot possibly allow. The horizontal asymptote now Again, we recognize it's going to be at 0, and we had a little bit of an explanation as to why. Basically, the horizontal asymptote really only exists out here and out here. That's what we're concerned with. And so once again, if I'm looking at the y values that I have here, well, they're off the screen, but they're extremely high and positive. And so I'm getting some extremely large values that we're dividing into 1. So this is 1 over some extremely large value, extremely large positive value. And so I know my graph will be sort of this one. And then on the other side, exactly the same thing. I've got extremely large positive values. I'm dividing 1 by those extremely large positive values. I'm getting a positive value very, very close to 0. And so that's just, again, the understanding of the horizontal asymptote. We'll see them more in another section later on. But the key is to recognize that really I'm only interested in horizontal asymptotes at extremely large values of x or extremely large negative values, negative 10 billion, things like this. In the middle of the graph, it turns out that the horizontal asymptote can be passed through. We'll see that in some examples later on. Then as we go through, we'll sort of work a little bit left to right here. My graph, where my graph is increasing, where my graph is increasing, my reciprocal will be decreasing and vice versa. So in this first section, kind of leading up to the first vertical asymptote, my graph was decreasing, and recognize, of course, somewhere out here the graph still exists. It's just off my page. So my graph in this whole negative section up to whatever this first vertical asymptote is, or wherever this first vertical asymptote is, that whole section will have my original graph decreasing but positive. And so my new graph will have to be increasing and positive in that section. And then the one key value that we sort of want to make sure we remember is right here is a y value of 1 in my original graph, and so I'll hit that same point on my reciprocal. So my reciprocal is going to look something like this. It's going to go very slowly and then shoot up here, and of course I can't draw it really well, but that's the basic idea of what's happening in that first section. In the middle section here between my vertical asymptotes, I'm going to have key values at -1. I have a local minimum here, and so in line with that will be my local maximum, and I don't know exactly what it is, but it's somewhere around here maybe. And you can sort of see my graph is already kind of forming, but if we just think about the last little bit, in this section right here, my graph is negative and decreasing, so my new graph must be negative but increasing, basically like this. And of course the opposite is true in this next little section. My original graph is negative but increasing, so my graph will remain negative and decrease to fill in this basic area. And then the other side of the graph is similar to what we've talked about already. My graph is on the right side of the second vertical asymptote, increasing and positive, so my new graph will be decreasing. Oh, make sure I don't forget about my lucky 1 here. Decreasing and positive, and looking something like this. Okay, so hit them on all the little parts. Horizontal asymptote, vertical asymptote, increasing becomes decreasing, decreasing becomes increasing, positive remains positive, local maximums, local minimums interchangeable, and the 1 and -1s will be intersection points. If the original graph crosses at a y value of 1, 1 divided by that same 1 will also get me a y value of 1 on my reciprocal. Okay, so that's the basics of how reciprocals work, but again, the very, very important key is just to do the math, recognize the math. That's what I'm calculating. Again, really 1 over the original y value, and then I shouldn't have any problem figuring out what's happening in each case.